Welcome to Learn with Roblox. In today's video, we're going to cover expected value. Let's take a look at this first problem. It says, in a game, you win $1 if a coin lands on heads, and $3 if a coin lands on tails. If the coin is fair, what is the expected payout per flip? So this is an expected value problem. And how do you calculate the expected value? What you do is you take each value and you multiply it by its probability. And then when you're done with that, you add up all the results you get. Let's talk about what that means in the context of this problem. So first off, there are a couple different values. We know that we get $1 if the coin lands on heads. And we also know that we get $3 if the coin lands on tails. And then now we need to find the probability of these values. Well, it said this is a fair coin, right? And when you flip a coin, there's a 50-50 chance that it lands on either heads or tails. So the probability that you can assign is 50%, or I'll just write that as 0.5. Because whenever you're doing expected value problems, your probabilities need to be either decimals or fractions. You can't use percentages here. You have to convert them. So I'm going to write 0.5 for both of these values because there's a 0.5 chance you get $1 and there's a 0.5 chance you get $3. Then now what do? You multiply each of the probabilities by its corresponding value and then you add them all up. So let me do that. That'd be 0.5 times $1. And then we need to add that to 0.5 times $3. And now we can just compute this. 0.5 times $1 is just $0.5. Let me just write that here. And then 0.5 times 3 is just 1.5 or $1.5. And 1.5 plus 0.5 is just 2. And this is in dollars. So therefore, the expected payout per coin flip is $2. I want you to notice something. Notice how on each flip, you can't get $2. You only get $1 or $3, but somehow the expected value is $2. What does that mean? Well, basically, what an expected value means is that whenever you do something many times, on average, that's the value that you would get. So if I were to do this coin flip 1,000 times, or maybe 1,000,000 times, on average, I receive $2 per coin flip, even though that isn't a possible amount. So this is a key concept. The expected value may not be a possible value. Let's go on to some different problems. The second problem says there are 2 green marbles, 4 red marbles, and 5 blue marbles in a bag. Green equals $10, red equals $2, and blue equals $3. Find the expected payout if you draw 1 marble from the bag. If the game costs $5 to play, is it worth it? So let's find the expected value of drawing a marble from a bag, or how much money I would make on average. That's what an expected value is. So what we need to do is we need to fill out the value and find the probability of that value. Let's start with the green marbles. So for the green marbles, it says that there's 2 green marbles in the bag, and there's 2 plus 4 plus 5 blue marbles in the total bag. That's 11 total marbles. Therefore, the probability of getting a green marble, assuming that we randomly pick one, that's just 2 out of 11. And the value of a green marble is $10, as it defines it in the problem there. Now let's go to the red marble next. It says that a red marble will give you $2. And how many red marbles are there? There's 4 red marbles out of 11 total ones. Therefore, the probability of picking it is 4/11. And finally, we can move on to the blue marbles. It says that a blue marble will give you $3. And there's 5 of these. Therefore, the probability of drawing a blue marble is 5 out of 11. Now, what we can do is we can just use the formula, which is just multiply the value by the probability of getting that value and then add everything up. Let's do that. So first, I'm going to do the green part. That's 2/11 times $10. Next up, we have to do 4/11 times $2 for the red marble expected value. Finally, we have 5/11 times $3. And now let's just compute these and add them up. So I'm just gonna do this all in green here. So for the first part, 2 out of 11 times 10, that's about 1.818. And then 4/11 times 2, that's just about 0.727. And then 5/11 times 3, that's about 1.090. And then if you add all these up, I'm just going to round it to the hundredths place since we're dealing with money here. That's about $3. and 64 cents. So therefore, the expected value of money that I would make when I draw a marble in this game is $3.64. Now, the second part of the question says, if the game costs $5, is it worth it? Well, think about it like this. On average, you're earning $3.64 each time you draw a marble, but that is less than the $5 it costs to play this game. Therefore, on average, it might not be a good idea to play this game. So the answer is no. That's not to say that you're going to lose money every single time, because it's true that on some of the draws, you might get lucky and choose a $10 green marble, but on average, you're likely to lose money. That's what this means here when it says that 364 is less than $5. So on average, no, you probably should not play this game. This third problem says, a chocolate company is doing a promotion where 1 in 500 chocolate bars will have a $100 bill inside of them. If each chocolate bar costs $2, what is the expected loss from buying a chocolate bar? So what we need to do is we need to define the values and the probability of those values. First off, we know that if we buy a chocolate bar, you could win $100. That's the value. But what's the probability of that? Well, the probability is just 1 out of 500. Because it said that 1 in 500 chocolate bars will have this. So that's the probability. It's just 1 over 500. Now, there's another value that you need to think of. It says that each chocolate bar costs $2, right? And to get this $100 bill, you'd have to buy a $2 chocolate bar, right? And if you're buying that chocolate bar, that's minus $2, right? Because we're losing $2 to buy this chocolate bar. And what's the probability of this? Well, if we buy a chocolate bar, we're guaranteed to lose $2, right? That's how much it costs, unless you're stealing, but I wouldn't encourage that. So the probability of this is 100%, or you can just write that as 1. And then now all you need to do is multiply the values by the probabilities and then add them up. So let's do this here. So first we have 1 over 500 times $100. And then we have to add that to 1 times minus $2, because you're going to lose $2 every time you buy a chocolate bar. And now we just compute this and add 1 over 500 times 100. Let me just rewrite this as 100 over 500. And therefore, that's just 1/5. And 1/5 is just 0.2. And then 1 times -2 is obviously just -2. Oops. And then 0.2 minus 2 is just -1.8. So let me just rewrite that minus sign on the outside and put a dollar sign in here. So this says, on average, if you bought lots and lots of chocolate bars, you would lose $1.8 for every chocolate bar. So this is our expected value. This problem says you're on a game show and they have a wheel to spin. There's a 50% chance that you win $30, a 25% chance that you win $50, and a 25% chance that you lose $20. The host offers you a chance to walk away with $25 without spinning the wheel. Should you take his offer? So to see if we should spin the wheel or take his $25 offer, we need to compute the expected value for this wheel, or just find out on average how much money would we win if we spun this wheel. So I've drawn the wheel here, and you see that $30, that's 50% chance, minus $20, that's a 25% chance, and plus $50, that's a 25% chance. So now let's go up to the table up here and fill in these values. So I'm just going to fill these values in one by one. So first, we could win $50 from this wheel. We could also win $30 from this wheel. But we could also lose $20 from this wheel, so that's minus 20. And then just fill in the probabilities. So for winning $50, there's only a 25% chance of that. So write that as 0.25, because you can't use percents for an expected value calculation. For $30, there's a 50% chance, or that's just 0.5. And then for losing $20, there's a 25% chance, so 0.25 once again. Now all you do is multiply the value by the probability and add that up for every single value and probability. So let me just go down here and do that. So we have 0.25 times 50 plus 0.5 times 30. And then we're going to have minus 0.25 times 20. I put the minus sign on the outside right over there. And then now we just need to compute this. So 0.25 times 50 is just 25. Or no, that's 12.5. And then 0.5 times 30 is just 15. And then minus 0.25 times 20, that's just minus 5. And then now if you do 12.5 plus 15 minus 5 and compute that, what you're going to get is that that's just $22.5. So all this says is that on average, if you were to spin this wheel, you would earn $22.5. Now, should we take the game host's offer or not? Well, that is less than the $25 that he is offering us. And because of that, we should not spin the wheel, because on average, we would make less than $25. So it might be in our best interest to take the 25 and just go. This problem says, Steph Curry has a career 3-point percentage of 42.3%. Suppose you get $4 for every 3 he makes and lose $3 for every time he misses. What would the expected payout or loss be after 10 3-point attempts? So to this problem, let's define the values and their probabilities and use that to find the expected value for just one shot. And then what we can do is once you have one shot, we can find the expected value for 10 shots that Steph Curry takes. So first, the values are you could win $4 because if he makes a basket, you get $4. And if he misses the 3-pointer, you're going to lose $3. So that's minus $3 there. And now we need to find the probabilities of these. So the probability of making that 3-point shot, that's 42.3%, but you can't use percentages for these types of problems. You need the decimal. So just divide that by 100 to get a decimal. And if you do that, that's just going to be 0.423. Then after that, to find the probability of missing a shot, well, the probability must add up to 1 because you either miss a shot or you make that shot, and that must add up to 1 for the probability. So just do 1 minus 0.423 to find the probability that Steph misses this shot. And if you do that, you're going to get 0.577. And now what we can do is we can multiply the values by the probabilities and then add that up to see the expected payout for one shot or expected loss. So let's do that. So first we got to do $4 times 0.423 and then plus minus $3 for every loss or every basket that you don't make or that Steph doesn't make times 0.577. Now just compute this. So 4 times 0.423 is about 1.692. And then minus 3 times 0.577 is negative 1.731. And then now we just need to subtract those two numbers. And if you do that, that's negative 0.039. So this is the expected loss for every shot Steph Curry takes if we're paid $4 for every basket he makes and we lose $3 for every shot that he misses. So on average, we would lose a bit of money in this game. And then to find the expected payout or the expected loss after 10 shots, just multiply that 0.039 by 10 because we're doing this 10 times now. So let me just rewrite that. We just need to do 10 times negative 0.039. And then when you do that, that's just going to be negative 0.39. I just get rid of the minus sign and put a dollar sign there. And then put the minus sign on the outside. So this is it. This is our expected loss after Steph Curry takes 10 shots. This final problem says, you decide to cheat the big bass wheel at Chuck E. Cheese and force it to give you 1,000 tickets. However, if the staff catches you, they will confiscate all your tickets, 2,350 currently, and ban you for life. If the chance of getting caught is 39%, what is the expected payout or loss in tickets of the shady maneuver? So to solve this expected value problem, or expected tickets problem, what we need to do is define the values and the probability of those values. So first, we could get 1,000 tickets, and that's if we pull off this maneuver. You could also lose 2,350 tickets if you get caught. So we're going to put minus 2,350 because we could lose those tickets. Now we need to define the probabilities of those. Well, we know that the probability of getting caught is 39%. So for this minus 2,350, I can just put 0.39 because that's what 39% is as a decimal. And then to find the probability of success in winning those 1,000 tickets, just do 1 minus 0.39 because the probabilities have to sum up to 1. And if you do 1 minus 0.39, that's just 0.61. And now all we need to do is just multiply the probabilities by the values and then sum up all the results. So let me go down here and do that. We have a 0.61 or 61% chance of winning 1,000 tickets. So 0.61 times 1,000. And then we have a 39% chance of getting caught, and this will cause us to lose 2,350 tickets. And then now we just compute this. So 0.61 times 1,000 is 610 tickets. And then 0.39 times negative 2,350 is just minus 916.5. And then if you do 610 minus 916.5, that just ends up being minus 306.5. So minus 306.5 tickets. So on average, if you were to do this maneuver many times, even though you can probably only pull it off a few times before you get caught, on average, you would lose 306 tickets, or 371 to round it up, I guess. So overall, you probably should not do this. This would be a bad idea because the expected value is a negative number. If you enjoyed this video, please consider leaving a like and subscribing. Thanks for watching.